Okay, I'm going to go through the rapidly varied flow Excel spreadsheet. Right, let's first get down to where I'm getting it from. Learning resources weeks 3, 4 and 5, Excel calculation tools for open channel flow. And we're going to go down, passing these videos to get the rapidly varied flow specific energy calcs. So click on that to download it. You can do the 3 buttons, download original. Also, I'm just going to import this cubic solves function, so go to that and click download original file to get the cubic solves.bas file, which is inside the zip. Look at the other videos for the details on that. So if I open that file now, and I'm going to open a copy I've already got. Okay, so week 2-3 rapidly varied flow specific energy calcs Excel SX. This hasn't got the cubic solves .bas function in yet, but we're going to include it. So just recap of what was in the last video on the slides. I'm going to type this function in this box so we can draw a function of the cubic. So let's go there. E equals A, which we'll fix with the dollars, times y cubed plus B, which we'll fix with the dollars, times y squared plus C fixed with your dollars star y. I mean, it's always going to be 0, so it's not necessary that, but we'll leave it in for a full cubic function plus D, which again we'll fix. Okay, second cell in this Y column, so we've got one dot on there. Second cell in the Y column will be the 1 plus delta Y, which we're just going to use as a variable, so this will allow us to change the graph a little bit. And I'm going to fix that dy A11, and if I drag this one down, I'll get 2 points. I'm going to drag this down a little bit further. Okay, let's just click on that graph. Let's see if I can actually drag these down to about cell 35. Yep, cell 35, and we get a full graph. Remember, what we're always looking for is where this crosses the x-axis. Well, it doesn't, so let's have a different start point. Let's have a minus 0.5. We know there's going to be a negative solution. Okay, so it goes from negative y, negative function value, to positive, and just crosses there as well. It goes, all this bit here is irrelevant, so maybe we can change the dy a little bit. 0.05. Yeah. Okay, it doesn't quite go to the right over there, so 0.08, bit much, 0.07. Okay, so we can clearly see the 3 points where it crosses the axis. So looking at that, we can see that the solutions are between minus 0.34 minus 0.36. So we're looking for a change in sign here. So minus, we're seeing the solution at 0.55, between 0.55 and between 0.62, and another solution there's change sign between 0.9 and 0.97. Okay, so we can program in our secant function over here. We've actually got the function nicely typed in, so copy and paste it here and here. Secant function, we need to type that in here. That's this secant function here. So y I minus 1 minus the function of y I minus 1 times, I'm going to have to put 2 brackets here, y I minus 1 minus y I minus 2 divided by bracket function of y minus 1 minus the function of y minus 2. That's the next guess there. Let's just pull the function down. Nope. And we're trying to get that towards 0. Okay, so between, well, near 0.1, 0.5, minus 0.5 and 1, we know that there's 3 solutions. Secant method has come up with this 0.95. So we can put in our values for y2. I could call them y21, y22, y23. They're all solutions. Let's put that in there. 0.9586. We want it to get it to converge to a different one. Say if I put a 0 in that one, that's converged to about 0.3 minus 0.36. And we need the one that's missing, the one that's near 0.5. So let's try 0.5. Okay, yeah, that's good. That's converged to my 2.5852. Okay, 3 solutions we've got by hand. Well, we've got by drawing a function so we can see where they are. We've got by guessing the initial values in the secant method. This is perfectly acceptable to do. I did write a Visual Basic function to do this calculation for you without typing. It's exactly the same as this block of Excel here, so you can use it or not, but it's not working at the moment. And I also wrote a function called get highest cubic depth, which would get the highest number of these 3, or attempt to. It's not infallible, but it will attempt to get the highest of these 3, because the highest is often the one we want. Okay, so how do we get this working? Well, we need to incorporate the cubic sols.bas function. So I'm just going to do that. Now the easiest way is to go up to your menu at the top, click developer, but you may have seen that developer is not always there, so we need to go and make sure it is showing. So file, options, customize ribbon, and make sure developer is ticked. Click OK and it will show there. Click on developer, click on Visual Basic because it is Visual Basic, and this window pops up. Now this one here is my worksheet that I'm working on now, and I see the list of all the worksheets in there. I need to insert a module, not a user form nor class module, a module. Oh, that's not right. I need to import file. I need to go and find that. It's in my courses. I've got a lot of courses. Let's find 3415. It's in my lectures 2425. Excel cubic sols.bas. So I'll find that .bas file, which is I've unzipped from the zip. Open it. Not showing it on the screen here, but it's now appeared under this modules section. Click on modules, open it, double click to show, and now I see the secant cubic and the get highest cubic depth. Okay, that's all you need to do. Never need to look at that again. Close it. But we do need to save the file, and we need to save it as a macro enabled file. So save as, and we select XLSM and not XLSX. XLSM. If you save it as XLSX, it will lose this Visual Basic. So we save it as an XLSM file, and that warning message goes. Okay. If I click on this, still showing not working, but if I go up and click on the function there and press return, I've got non-convergent divide by 0. Oh, it's not done. It didn't like some things in that function, but it safely calculated an answer, which was happens to be the highest cubic. And how it's done that, if I look at that, I see that the parameters, we've got the 0.001 as a tolerance. That's how accurate it's going to be, to how many decimal places. The maximum of iterations, how many it's going to try. We see up here we had 4, 8. It's going to do 10. Y1 and Y2 was 1 and 2. Let's see if I put the same values in here of 0.5 and 0, what it got to, and it got to the 0.58353, same as here. So to the third decimal place, we could increase the last decimals there. Oops. Okay, this is working to probably a higher tolerance than the secant method there. Get highest cubic, not working, but we're going to click up there. We look at the parameters that you can put in there. You put in the ABCDs, you put in the intervals. That's how many times it's going to try between the maximum and the minimum. So 0 and 2, so we'll split it into 30. Okay, try a higher number if something's not working, but 30 works about right for most calculations. I'm looking for something between 0 and 2. Again, not infallible, but we'll try that. And it's come out with the highest of these 3 solutions here, which is what it's intended to do. Okay. So we might use this calculation sheet again for the next energy calculations. Let's go and see the first one. E over a bump, EG1, example 1. So here is the example. Example 1, steady flow in a rectangular channel of width 5 meters, interrupted by presence of a hump or bump of 0.2 meters. In the channel, upstream depth is 1.25 meters and the discharge or flow rate is 10 meters cubed per second. Find the flow at position 2, which is here on top of the bump. So I've taken the known values here and put them in my yellow cells up there, and we're just going to go through and do the calculations. So here we have lowercase q. Remember, lowercase q is flow per unit width, so it's just capital Q. So we need an equals capital Q divided by width. We don't need to fix anything because we're only going to use this value once. The velocity, well, that's flow divided by area divided by B times Y. And the Froude number. What's the Froude number? Can you remember the Froude number? Well, I'll put over to the right here 3 different ways of calculating the Froude number. We could do this one, which is nice and easy, and square root it, but this is quite easy as well. V over root gy, gy for a rectangular tunnel. So equals velocity divided by the square root of g times the depth. Froude number 0.46, no units. Subcritical flow, we can calculate the energy. This is the energy upstream before it going over the bump, is equal to the depth plus v squared over 2 divided by g. 1.380 meters. Now the energy is not going to be lost. it's going to be conserved, so it's balancing energy in this equation that we're going to solve. What's the unknowns in here? Well, we can work out, relate V2 to Q and write it as a function of depth. We know dz because we've given it 0.2. The only unknown is going to be y2, so we're going to calculate y2 from this function. A second. Right. We need to calculate a function like this one. It's going to be a, b, c and d. So a will be 1, always 1, we don't need equals, so actually 1. B is equal to all this bracketed term here, so b is equal to delta z minus y1, minus lowercase q squared divided by 2 divided by g divided by y1 squared. You might think that formula is not right, you need to put some brackets in there, but actually this will work. You can try it yourself. Minus 1.180. C is equal to 0 always in these energy calculations, and D is equal to this Q squared over 2G. Q squared divided 2 divided by G 0.203874. I'm not putting any units on here, not necessary. We can put these values into our function. Actually, these are the values in our function, so we actually know what the solutions are going to be. And, let's go and see here. We have the negative one. Let's put the negative one in here. So not that interested in. The other were 0.5852. And the highest one, which actually we are interested in, is 0.9. Well, what are we interested in? Let's see why I say we're interested in that. The solution's got to drop from 1.25 because it's subcritical going in. It's got to drop, but it can't drop below critical. Well, we're not calculating critical depth here, but we may need to check it. We expect it's going to drop to here. We expect that this 0.585 is below critical. Well, let's calculate critical depth here. And what's critical depth? Critical depth is when Froude number equals 1. So if we take one of these equations here, we can calculate critical depth here from this function. So equals, and put some brackets on here, q squared divided by g all raised to the power of third, and put those in the brackets. I could use 0.03333. That would be good enough. 0.724. 0.7242 is between these two, which is as it should be. So we can't go below that, so it's not going to be 0.58, it's going to be 0.9. The answer is going to be 0.959. Let's do a couple of checks. Check what the energy is at these two values, because it should be the same. But it's an additional check to for you to see that you've got your calculations right. Remember, energy calculation is this one. And it's equal to y. The y we've got, I'm going to do these two y's, y plus, I'm going to do q squared divided by a squared, formula on there, divided by a squared, and a is the y we've just calculated, times the width. So that's v squared divided by 2 divided by g. 1.181. Now you might think, why is that not the same as that? Well, we'll see that in a moment. Let's calculate the second solution. So it's the y3 plus q squared divided by y times b plus 2 slash g. Okay, mistake there, because that has to be squared. Okay, minor differences in the precision there. Don't worry too much, I don't think. Okay, so the precision's slightly similar. So what we want to see is that these two plus delta z are equal to E1. So E1 is, let's put that in there, E2 plus delta z would be that one plus the delta z, that's correct, or that one plus delta z, it's the same. Okay, I'll just increase the precision there and we see that they're the same. Meters, units. Okay, simple calculation, but the objective was to calculate y2. So let's see, the second example was to calculate the height of the bump which would cause critical depth in the channel. So set up as we did before. We've got a width, so we've got a flow rate going in. We've got a width of the channel, rectangular channel. We've got a depth of the upstream flow. We want to know the depth downstream, y2, and we want to know the height of the bump, which will cause critical depth. So this y2 is going to be critical depth. So let's just calculate Q again. Lowercase q, which is flow per unit width, Q divided by width. It's 2 meters in this per second. Meters cubed per second per meter. V is equal to Q divided by B times Y, which is 0.8. It's also, we could say, it's also equal to Q divided by Y, 0.8. The Faraday number we can calculate from this formula here. We want to know whether a sub or supercritical flow is key. That's why we're calculating the Faraday number. So it's velocity divided by the square root of g times the upstream depth, 0.16, very subcritical, very slow. Critical depth, well, we equate that third number to 1 to find the y, which would give us 1, but we can do that with this formula to calculate yc directly, so we'll do that. It's equals bracket q squared, so lowercase q squared divided by g all raised to the power of third. I'm just going to put 0.3333 in here, and that'll be close enough. And E is this calculation. We always need E, so let's do the calculation if we're not sure when we're going to use it yet. Actually, it's E1, so it's not that YC I've just calculated, it's E1 plus the V1 squared divided by 2G, 2.533 meters. It's critical over the bump, so Y2 equals YC equals the YC that we've just calculated. So that's the height over the bump. Energy at 2 will be the energy at that depth. Okay. Let's see this energy calculator we're going to do. It's well, let's just calculate V2. V2 is Q divided by Y divided by B. 2.67. Got the units wrong there, meters per second. Meters per second. E2 is equal to Y plus V2 squared divided by 2 divided by G. 1.112 meters. Now the two energies need to be the same. This is not actually E2, it's E2 plus Z. Plus the delta Z is equal to 2.55, so let's just say that E1 equals E2 plus dz. Get my fonts in there, it's correct. So delta Z is equal to E1 minus E2, 1.420 meters. So a bump of height 1.420 meters will cause critical depth in that channel. So that's quite a high bump. Okay, so the next example is looking at uniform flow in a 3 meter wide channel. I think I'll record this in the next video.